Hi folks, today we're going to be going over the 55s. Likely there will be two videos to watch for the 55s because it's kind of a long topic. I would encourage you with most questions to pause the video, see if you can answer the question, and then go ahead and see what the answer is. You'll learn a lot more that way than if you're just writing down stuff. So the very first thing that we need to know is that these brackets represent concentration or molarity. So if I wanted to use this, I would say, so the concentration of the hydrogen ions are this. So the concentration of the hydrogen ions are that. In pure water, or when a solution is neutral, what must be true of the concentration of the hydrogen ions and the concentration of the hydroxide ions? This would be one of those times that you would pause the video and see if you can answer the question. They would be equal to each other if the solution is neutral. In an acidic solution, circle the one that is more concentrated. Again, this would be one that you pause the video and see if you can answer it. And I'm going to stop giving you that message. In an acidic solution, you better have a higher concentration of hydrogen ions. Otherwise, the solution is not acidic. In a basic solution, circle the one that is more concentrated. Well, if it's basic or alkaline, you better have more hydroxide ions than hydrogen ions. For the rest of the calculations, it may be useful to find your scientific notation button on your calculator. So pull out your calculator, pause the video if you need to do so. Many times you're going to have to press the second button, and then right next to the second button there is a button that says SCI/ENG. That's how you're going to put your calculator into scientific notation. So you'd push the second button and then you would push the SCI/ENG. If you have some older calculators or some calculators that are not the variety that we have in classroom, you might have to search around for that science button, scientific notation button. Find yours now and let your teacher know if you were in class if you could not find it. If you can't find it ever, you're definitely going to have to come in for some assistance. So what I want you to do is to type this number into your calculator. And then I want you to switch your calculator to the scientific notation way. And again, that's pushing the second button and the scientific notation button. And then if you hit enter after you have that number in, hopefully you see something like this, which means 1 times 10 to the negative third. Play around with that. Make sure you understand what you're doing there because that's going to come in handy in a little bit. So number 6, pure water has a hydroxide ion concentration of 1 times 10 to the negative 7th. What's the value of the hydrogen ion concentration? On the cover, on the front cover of your unit pack, you have this chart that's right there. And we're going to be using this formula that's right there. So this is a bit of algebra. The hydroxide ion concentration we know is that number right there. We know this number, and we're solving for that number. So if algebra is rusty, I'll go through it real quick with you. So we have our hydrogen ion concentration. We know our hydroxide ion concentration is this. And that all has to equal 1 times 0 times 10 to the negative 14. So I have to get the hydrogen ion concentration all by itself on that side. So to do that, I divide this side by 1.00 times 10 to the negative 7th. I do the exact same thing here, 1.00 times 10 to the negative 7th. And I get my hydrogen ion concentration all by itself on this side. I would like you to try this on your calculator and make sure that you're using your calculator correctly. If you are using it correctly, you will get this on your calculator. So 1.00 times 10 to the negative 7th. So that would be my hydrogen ion concentration. Play around with your calculator, make sure you can get that. If not, you're going to have some issues as we're moving on. 7. If the solution had a hydrogen ion concentration of 1.00 times 10 to the negative 6, what would be the hydroxide ion concentration? So we know this part right here, and we know this part right here, and we have to solve for the hydroxide ion concentration. Go ahead and solve that. Pause the video as you do so. The answer in this case would be 1.00 times 10 to the negative 8th if you punched everything into your calculator correctly. Again, the formula that we're using is right on the front of your cover. You will always get to use that on quizzes and tests. 8. What is pH? pH is the measure of the hydrogen ion concentration. So that is what pH is a measure of. How many hydrogen ions do you have there? So what's pOH a measure of? Well, that's a measure of the hydroxide ion concentration, or how many hydroxide ions you have. What is the pH of a neutral solution? 7.0, throw a repeating mark above that 0. That's when it is neutral. And then what's the pOH of a neutral solution? Well, same thing. 7.0 with that repeating mark above the 0. So what is pH plus pOH? That chart that is on your cover has the formula right at the top of it. It says pH plus pOH adds up to 14.0. So what would be the pOH of a solution that had a pH of 6? Well, put that pH right there. 6 goes right there. All has to add up to 14. So if you manipulate this, you can end up having 14 minus 6.00 to equal your pOH. You do that math and you get 8.00. I ask you to go to 3 sig figs, and I'm going to talk more about that later on. Go ahead and try number 13, see what you get for an answer. Your answer should be 5.50. In most solutions of weak acids and bases, the concentrations of the hydrogen ion and hydroxide ion are very small. To allow for easy comparisons of small values of hydrogen ion, a logarithmic system was developed called the pH scale. The scale goes up by multiples of 10 instead of multiples of 1 to make it a more compact scale from 0 to 14. Do realize, folks, that the actual pH scale does go below 0 and does go above 14, but for items that students would handle, 0 to 14 seems to be the most useful. So the 0 to 14 scale is useful. It's very compact. If we did go up by ones, we would have to go from 0 up to 100 trillion. Way more broad way of looking at this same topic. So 0 to 14 seems to be the most useful. And again, the pH scale does extend below 0 and above 14. 15, which is a smaller number, 1 times 10 to the negative 4th or 1 times 10 to the negative 5th? Circle your answer, and I will reveal it. Well, if I write both in decimal form and I look at it this way, I can see that this number is 10 times bigger than this number. So what is my smaller number? It is this one right here. The one that has a larger negative exponent is my smaller number. Which has a lower pH, or which is more acidic? Take some time to think about this. Well, this is my bigger number, and it's hydrogen ions. So if I have more hydrogen ions, I should be more acidic. If I'm more acidic, my pH should be lower. So again, I'm looking at these two numbers. I'm seeing that this number is larger. It's 10 times larger than this number. So if it's larger, it's more acidic. If it's more acidic, it should have a lower pH. And this is my answer. So here's a neat thing with the pH scale and hydrogen ions written in scientific notation. The exponents tell you roughly what the pH is. For example, if the hydrogen ion concentration is 1 times 10 to the negative 4th, the pH would refer to the exponent. So the pH in this case would be 4. Kind of neat. If the hydrogen ion concentration is 9 times 10 to the negative fourth, the pH would refer to the exponent again. So the exponent in this case, again, is a 4 negative, but this number out front's not a 1 like the last problem, so it changes our number a little bit. If I do the mathematics of this, the pH is 3.05, which is close to 4. So again, when I'm given hydrogen ion concentrations, the exponent gives me an idea of what the pH should be. 20, if the hydrogen ion concentration is 1 times 10 to the negative fifth. So if we start with a 1, that exponent tells us our pH, so our pH in this case is 5. Another example that's on your paper, I do the same number except for I put a 9 out in front instead of a 1. My pH should be around 5, and when I do the actual mathematics of it, I get 4.05, which is around 5. What would be the pH of an acid with a concentration of 0.00100? First, I would convert it to scientific notation. So this number would be 1.00 times 10, and I have to go 1 spot, 2 spots, 3 spots with the decimal, and it's smaller than 1, so that's to the negative third. My number out front is 1. My exponent is 3, so my pH would be 3. I'm going to end up shutting this video down, and you're going to have to open up the next video to do the rest of the questions.